Hello students, Guillaume here with another R video. This one is all about simulations. So we know already how to simulate from distributions that are implemented in R, but I want to do a bit more and specifically go over some of the situations we've encountered in the theory part of the course and see if we can reproduce them with simulations. And there's a few different things I want to cover, so I'll go bit by bit. The first thing, I imagine you've seen this before, is to cover how can you simulate from a distribution you know exactly what the CDF is, but it's not implemented in R. So you don't have a R function already. You know, I think you know what I mean. R gamma exists, right? So I can simulate, let's say 10 gammas with whatever shape I want, okay, and whatever rate I want. But we'll use the Pareto example here because, and by the way, you can always find some documentation. If I type R gamma here, in R, you're gonna get information about this distribution. But for example, there is no R Pareto. Okay, at least in the base version of R, I think there's some packages with the Pareto, but in the base version of R, it doesn't found it. Okay, so now how can we simulate from the Pareto distribution? That's the first task we want to do. And we're going to use this this trick here. That this is a thing I said maybe you've seen before. There's a method called inverse transform sampling. So in essence, let's say that you have the CDF of certain random variable, okay, fx, okay, where x would be the random variable, and it has an inverse, okay, let's call it just qx here, but it's the inverse of the CDF, so you can call this the quantile function. If you take an observation, a random variable u, which is a uniform 0, 1, then qx, the function, the quantile function evaluated at u, well, you can see this whole thing, qx of u, as a random variable. Yes, it's a function in which you feed a random variable. It's again a random variable. Well, this random variable has the same distribution as x. Okay, so this random variable as CDF fx. Okay, if you don't believe me, well, you can maybe look at the reference. Let's go to our favorite reference, which is Wikipedia. Okay, you can read about this here inverse transform sampling, and you see, of course, you have a lot of information, but this is what I said. If x is a random variable, you take its inverse. Okay, we're gonna see a continuous case, so there's no ambiguity about what inverse means. Of course, if you have a discrete, it's just slightly more complex, but you can take what's called the generalized inverse. I'm not gonna explain this before, but maybe you've seen this before. I mean, I can click on the link. Generalized inverse is simply that you take the infimum, okay, of x. So it's the smallest possible x such that the CDF at x is bigger than p. Okay, so the generalized inverse, so the inverse of a CDF, the quantile function at p, you take the smallest x, which makes the CDF at this x at least as big as p. Okay, but don't worry about this too much. Now let me just go back. That's what I said. F minus 1 is what I call q, the quantile function at u, as the same distribution as x. Okay, so now that we're clear on this, let's do this for the Pareto. So let's do this in a function. So remember, I call our Pareto doesn't exist, but I've got to declare it. So I'm going to create it myself. It's a function. I want to be able to generate whatever number of random variables. That's the first argument n, and then the other two are just the names of the parameters of the Pareto, matching what's on the formula sheet, alpha and lambda. Now, q is this quantile function for the Pareto. Now, how did I find this function? You just invert, I think, the CDF, okay? It's not hard to do. Let me just show you so we make sure we agree. I have calculations for this somewhere. Okay, this thing here. How do you find the inverse? Well, you start with the CDF. Okay, this is an expression of x. Set it equal to whatever, little u. Now, what the quantile function is doing is that you want to find the x that produces fx equal to whatever value u. Okay, and then you solve and you get a function of u. Okay, so said otherwise, what x makes the probability to be smaller or equal to that x equal to u? That's the quantile function. Okay, here it's a simple calculation. You solve for x. Okay, and you get to x equal this expression, so it's a function of u, and this red thing, I call it the inverse of the CDF, or the quantile function. Okay, so this is the function that's implemented in R. Over here. Yes. Okay, and so just as a comment, I'm declaring a function. Okay, Q is a function inside another function. There's no problem with that. It's allowed in R. I could have declared it outside, but here, because the purpose of this function is very specific to the generation of random Paretos, I prefer to declare it inside my Pareto, and inside my R Pareto function. And then what I do, very easy, I'm going to return Q, the quantile function of the Pareto, evaluated at a bunch of uniforms. Because I suppose I said from the beginning, that's the trick. We know how to simulate uniforms. Usually, every programming language will have a random generator for the uniform. So I leverage the power of the R unit function. If I feed to Q uniforms, it spits out observations that are from the Pareto. Okay, of course, because I've declared this Q to be the inverse of the Pareto CDF. Of course, this is applicable generally. So maybe in a tutorial exercise, I'm going to ask you to do this for some other random variable. Now let's just check that it worked. Arbitrarily, I'm going to declare alpha to be 3 and a lambda to be 4. Let's see what happens. I declare a sample here of size. What is the size? 100,000 using my new R Pareto function. Now, look in the formula sheet. With those parameters 3 and 4, the real expectation of the Pareto should be 2. Let's take the mean of my sample. Okay, you get something pretty close to 2. The variance should be 12. The theoretical variance under those parameters. Let's see. Okay, relatively close. You see, because the Pareto is heavy-tailed, there's lots of variations. It's hard to get accurate estimates, even with a sample size of 100,000. So you see, the variance estimate is not that close to the real value. Okay, let's try again. The mean, I'm going to get 199, and the variance again, it's not so close. Let's do again. Okay, you see, the variance is always kind of off. You can try with a bigger sample size, 1 million. It's going to take a sec. Oh, no, it's okay. You see, now it's a bit closer. Well, with 1 million, it's not too bad, but not always close. You see 11.52. Okay, let's just check quickly that we indeed have generated what we wanted. Random variables from a Pareto. I declare here the Pareto to be the density of the Pareto with alpha and lambda parameters. This just matches the formula sheet. Okay, again, it's a new function that I declare in R. And then I'm going to take the histogram of my sample, my Pareto sample. Okay, you see, it looks strange. Yeah, because the Pareto, as I said, is very, very heavy-tailed, meaning that even though the bulk of observations are between, I don't know, 0 and 10 or something, there's still some observation that are around 250 or 300. They're very few, but you still get some observation. That's why you get something very, very skewed like this. Okay, and if I put the curve of a Pareto, okay, I'm gonna see, seems to match though we don't see very well. So maybe you wanna redo this with the xlim parameter. So I'm just gonna check from 0 to say 20. Okay, I forgot. Yeah. Comma, and then okay, that's the shape from 0 to 20, and then let's see if it fits the curve of a Pareto. Yes, fits very well. Okay, that's about it for the generation of a random variable whose distribution you know, but is not implemented in R already. Another thing I want to do, so now you can take a break in your mind, we do something a bit different now, but always the theme for this video is simulations. Let's go back to a concept we've seen actually in week 1, which is mixture distributions. So recall a mixture is when you have the parameter of a distribution, which is itself random. So it's randomly generated. And then once it's generated from that now realized parameter, you simulate from another distribution. What's the unconditional distribution in that case? Well, we've done many problems where we find this under different circumstances. Let's focus on one, which is actually, let me just show you quickly in the tutorial booklet. It was one of those extra exercises, 1.8. So mixture, if x given lambda is an exponential lambda, but the lambda itself is random and has a gamma distribution, we've actually shown that the unconditional distribution in that case is in fact Pareto. So what I'm going to do now is just simulate this situation and just quickly check that indeed we have a Pareto, even though we know this, but it's for kind of, I suppose, pedagogical value. Let's do some simulation that match a situation we are already familiar with. So what I mean by simulating from the situation is simply this. We're going to simulate a large number of lambda. And then for each lambda, we simulate an exponential with that parameter. Okay, and then the resulting distribution of the x, all those x's we've distributed, which they all have a different lambda. But the resulting should give us a Pareto. Let's see. Okay, so here the parameters of the gamma, I'm going to call them little a and big B. Okay, little a and big B. So I'm going to do that in a function. Usually I like to do things in a function because then I can redo them easily by recalling the function with maybe different arguments. So this is just an arbitrary name I give to my function. Again, we want to do that for a large number of simulations. A and B are the parameters of the gamma. So first things, I generate a sample of the lambda parameters. Remember, the lambda has itself a gamma distribution. I can do that easily with the call to R gamma. And now every x is going to be generated according to an exponential with those different lambdas. But you can do that here we don't need a loop because R is nicely vectorized. So in one shot, with a call to Rx, you see I'm generating n times an exponential with a rate of what? A rate of lambda. But careful here, lambda is a vector, so it takes different values. But this works. R understands that, okay, you want n times an exponential, and each one you give me a different parameter. Just to make sure you understand what I mean, if I type Rx, and let's say that I want 3 of them, but I don't give it a rate of one thing. I give it a rate which is itself a vector, meaning, okay, the first observation, I want a rate of 0.01. Okay, so this observation should be quite big. Then the other one, maybe I want a rate of just 1. And then the last one will be a big rate, so the observation should be small. You see, it understands that I'm going to redo the same thing 3 times, generate an exponential, but each time with a different rate. And you see, of course, the first one is big, second one is not medium, I guess, and this one is small. Okay, closer to 0. Okay, so then with this x, I've generated exactly what I wanted, the mixture. Well, a sample of size n from a mixture. And let's just see if it works. At the end, I return x. Okay, return is just a command that says, okay, in the end, what is the function giving as an output? So let's try. I declare the function. I generate, I call this mix sample. So I generate a sample of size here 10,000. Let's try again with the same parameter, a equals 3, b equals 4. Okay, because this is exactly the situation we've simulated before. Okay, Pareto. But it's just that now we just check that this specific mixture exactly gives you a Pareto. So we know the mean should be around 2. Okay, very good. We know the variance should be around 12, but it's very variable around that. So yes, the estimate of the variance is very variable. Okay, you see it's actually pretty bad here because I had only 10,000. Let's try with 100,000. Okay, a bit closer. You do that a few times. Sometimes you're closer to 12, sometimes not so much. Okay, you see this illustrates how heavy tailed the Pareto is. sometimes just the random variation gives you observations that are so big that they're so variable that the estimate of the variance here is terrible for this specific sample I generated. Okay, and then lastly, what am I doing here? Okay, I'm doing some checks here. So here before I checked if the histogram fitted the density. Now let's do the same, but let's check the CDF just to vary things a bit and apply what we've learned in the first video or the previous video. So here I'm declaring simply the CDF of a Pareto. Again, this function doesn't exist in R, so I'm declaring it. Now here, I need to deal with the case where x is smaller than 0, the argument x of the CDF. Well, in that case, it's simple. The CDF should be 0. Okay. At the end here, what I call CDF is just a temporary variable that I'm going to spit out at the end of the function. So again, I deal with this case. Argument is smaller than is negative, then the CDF is 0. Otherwise, so you see in R the syntax if. So R checks this condition. If this is verified, then CDF is this. If this is not verified, then this is not executed and goes to the next thing, which is else. So if this is not true, else what should I do? I should do this. I should have the CDF be equal to the expression of the CDF of a Pareto you will find in the formula sheet. Okay, and that's it. Then I return CDF. Okay, so this gives me the CDF of a Pareto. Now, small thing. I'm going to vectorize this. So to avoid the need to have loops when I do my plots, I'm vectorizing the function. Vectorizing means that let me just show you. I declare P Pareto. If I type P Pareto of whatever value, okay, x equals 2 and with some lambda. Okay, let's just have the same as before, 3 and 4. That works. It gives me one value. So I've computed the P Pareto for 1x, but if I give it a vector, I think it's not going to work. Okay, it's not going to work because of those if-else things that are a bit complicated, but I can make it work explicitly by vectorizing my function, saying, okay, I want that this x, I want it to be possibly a vector. So R says, no problem, just vectorize your function and tell me explicitly that x can be a vector. Now, when I do that, okay, so I redefine P Pareto to be the vectorized version of my old P Pareto that was declared here. Okay, now this should work. P Pareto, yes, it computes 2 in one shot. Okay, I need that to be able to use the curve here, because this is what curve is doing. Curve is computing P Pareto for a whole series of x values. So I need the vectorization step. Okay, let's try. Here I'm plotting the CDF. Oh, and by the way, I think I forgot to mention that in the previous videos. Here, the syntax you might be surprised it works, but there's something in R that plot recognizes that. So this is a function in R. If I'm giving you plot ECDF of this, I want the ECDF on a plot. So this is working in the sense that usually plot, you need a x and a y usually. But here, I'm not entirely sure why, but the function plot recognizes that when I pass ECDF of a sample, it's fine. It's going to find itself the x and the y that corresponds to this sample. Okay, well, the x being the values and the y being the empirical CDF associated with the sample. Okay, so I get this. That's the empirical CDF. Then if I plot the curve of the Pareto, and I add it here, I think it it's taking a second because I have a big sample. If for some reason ECDF is a bit trickier to compute, so it takes a few seconds when you have a big sample. Okay, so it's right on it. Okay, so it works. Okay, next thing. Okay, now again, breaking your mind. Now we've seen. What have we seen? Generating from a new distribution that's not implemented in R, then generating from mixture distribution. Now we're gonna just generate a reinsurance example. A reinsurance example meaning from X, which is claims that are going to be here exponential, as we have done in the lecture week 2. Can I generate observations that are the payments made by the insurer and then the reinsurer? Yes, it's simple to do. So okay, n will be my sample size. Okay, I start at 10 just to show you. L will be, here I'm simulating exponential. L will just be the parameter of the exponential. So X is the claims themselves. They're exponential. Now M will be the retention. So remember, the insurer pays everything that is below 100, and then the reinsurer pays the excess of any claim above 100. So sometimes the reinsurer doesn't pay anything for a claim that is not exceeding 100. Okay, so if this is the claims, let's just generate one sample. Okay, now you see, of course, it's exponential with mean of 100. So some observations are smaller than 100 and some are bigger. Now, with simply this function pmin, careful, there is a function min, but it wouldn't work for what we want to do here. Here, I need to use pmin. I'm going to get payments made by the insurer, because you see X is a vector, but then I'm going to check X compared to every M. Well, not every M. I mean, M could be a vector as well, but don't worry about this. For here, M is not a vector. It's just a constant. So I'm checking every X against this single M, and I'm taking the minimum, but observation by observations. Okay, the regular function min wouldn't do that. The regular function min would just pick the smallest out of all the values you feed it. That's not what we want here. Here, this is what we want. So p min. Oh, I haven't declared my M. Okay, you see, gives me what I want, because Y for values of X that are smaller than X gives me just X, and then for this one, you see it's capped at 100. Okay, and same thing, the last one is capped at 100. Okay, and Z would be the opposite. What is the reinsurer paying? Well, they're paying the maximum between 0 and X minus M. Okay, and again, this should work. Okay, most of the time in this sample, they pay 0. Here they pay a little bit, and so on. Okay, now that's not overly complicated. I just want to check that if I simulate a large number of this situation, we can match the theoretical formulas we've derived in the lecture. Now here, of course, you might know that we don't need simulations, but I'm using a case that we've already covered just to make sure that we've done the simulations properly. So those formulas here, the what I call theoretical expectation of Y, they match the set of slides on week 2. Let me just show you quickly. Okay, so in week 2, we've done a few things around reinsurance. Eventually, we've shown this example. If X is exponential, what is the mean of, what is the expectation of Y, what a reinsurer pays? And we came up with this formula here. Same thing, we found explicitly a formula for expectation of Y squared, which of course allowed us to find an explicit formula for the variance of Y. Okay, so those are the formulas I've implemented in R. Okay, so I go back to R. Okay, this is the theoretical. Now let's just, I forgot if yeah, okay, I did simulate a bigger sample. So, okay, theoretical expectation is this, 63.21 with a sample of size 100,000. Okay, I get pretty close. Well, expectation of Z, we can do that as well. Theoretically, it would be the expectation of X minus the expectation of Y. Okay, I don't need to redo a bunch of calculations because, of course, everything not paid by the insurer will be paid by the reinsurer. So expectation of Z is expectation of X minus expectation of Y. This theoretically should be whatever this value is, and mean of Z, Z being the sample I have over there, is there. Of course, there's a bit of random variations, but we see we're pretty close. Here, I could easily generate 1 million, and you see we'll be very close, I think. Okay, we're very close. Here again, we're pretty close. And then Okay, and then same thing, you can check. This is a theoretical formula for the expectation of y squared. And then here, the empirical mean, if you take the mean of something squared, this is what I want. Okay, the second empirical moment, you see we're pretty close. Lastly, the variance, you can do the same thing. Okay, and we're pretty close. Okay, lastly, here I just computed the coefficient variation. We can just take a second to reflect. Should this be an increasing function of m or a decreasing function? Take a second. Should it be, if here I'm going to change m to 500, I'm going to recompute everything. Actually, well, those are, we can recheck that we get numbers that match in general, but the question, yeah, those numbers, they match, theoretical and based on simulated values. This should be bigger now because, let's check. Yes, I'm closer to 1. The insurer is retaining more of the risk, right? When m increases, the insurer is retaining more, so it's grabbing a portion of the risk that is far away on the right tail, or further away. So yes, the ratio of the variability to the expectation has increased. Okay, I think that's it. For the reinsurance example, it's not the time to call it a day yet. There's a few more things we need to show, and maybe the most interesting ones. Simulating under the individual risk model, and in fact, we're gonna revisit the last example in the slides for week 2. So let me just grab that example. So it's not overly complicated example, but in fact, we were left with a slightly unsatisfying answer when we did this theoretically, because we could not find the real probabilities that we were looking for. So just to remind you, this was the example where you have 300 fire insurance policies, but they're split into 3 groups, and in each group, the possible size of claims are different. So in this group, there's a maximum of 100K. In the second group, there's a maximum of 200K. In the last group, there's a maximum of 500K. Claims per policy are relatively rare, meaning every policy is going to claim with only 1% probability. And once they claim, then the size of the claim is uniform, okay, between either 0 to 100K or 0 to 200 or 0 to 500. Okay, and here we were simply, theoretically, we find some approximations to the probability the claims are 3 times as large as their expectation. Okay, the first question was we could find it explicitly. Okay, it's not hard to find the exact expectation, the exact standard deviation of the aggregate claims. So we might call this S. But here, what we couldn't find exactly is the this probability, and then we used normal and the log normal approximation, but we couldn't tell which one was better because we didn't know the real number. Now we won't find the exact number, but here with simulations, we can simulate a large number of S, here the aggregate claims, and then find, at least empirically, what's the probability it exceeds 3 times the mean. Okay, so let's do that. Okay, so here the situation is this: you have 100 person in group 1, 100 in group 2, 100 in group 3. The max claim size in group 1 is this, then this, then this. Whoops. And every group, the probability a policy generates a claim is the same, 1%. And this B, what I'm calling B, is number of simulations. So I'm going to simulate, in this case, 100K, 100,000 times S, the aggregate claims of all the people who are going to claim under this this scenario. Okay, and here I will use a loop. First step, okay, I'm just declaring an empty vector for S. Okay, so S is going to be a vector that's going to contain my 100,000 simulations of the aggregate claims. I need to declare it as being something, so I declare it. There's many ways to do this, but here I use just empty vector. Okay, now I'm doing the same thing because I want to simulate B times the same thing, so I'm going to do this in a for loop. Okay, because if you remember a for loop, is exactly what I want. Repeat exactly the same thing a fixed number of times. Okay, in this case, I'm going to repeat the same thing b times. Now, here you might note that we assume all the people are independent. So one way to simulate this situation is simply to say, well, okay, there's going to be a certain number of people who are going to claim in group 1. Okay, and then there's going to be a certain number of people who are going to claim in group 2, and then there's going to be a certain number of people who are going to claim in group 3. But this, all of those things are binomial. Here, generally, for the first one would be binomial. There's n1 trials, n1 people, and each one has a probability p of claiming. Okay, same thing for the second group, same thing for the third group. So this gives me the number of claims in each group. But that's not exactly what I want. What I want is the sum of money claimed in every group, and then I can sum those to find the global S. Okay, let me just show you at the bottom what I'm going to find. Okay, I'm going to review this, but at the bottom I'm going to find the sum of S1, the sum of S2, and the sum of S3, where S1 is the sum claimed in group 1, S2 is the sum claimed in group 2, and S3 is the sum claimed in group 3. But I want the total. Okay, you just need to deal with the case that n1 is 0. You need to deal with this case separately. Okay, because if n1 is 0, well, there's nothing to sum. No one has claimed. Okay, so if n1 is 0, then S1 is going to be 0. No claims. Else, so again, we use the if-else statement. Else, okay, so if n1 is at least one claim, then what is S1? Well, it's the sum of those random uniform claim amounts. Okay, remember in group 1, people are, once there's a claim, this claim is uniformly distributed between 0 and b1 being this number here. Okay, so if you understand that, I think you understand everything. That's how I simulate the total claims for the group 1. Then I do the same thing for the group 2. Okay, but now, of course, the random uniforms are between 0 and b2. I do the same for group 3. And that's pretty much it. Okay, at the very end, the last step, I find SI to be the sum of S1, S2, S3. Now, remember, we're doing this b times. We're doing this 100,000 times. So you see this index I is going to go from 1, 2, 3 up to b. So b times, I'm going to repeat those steps. Once this is completed, then I find SI. Okay, so I'm going to find S1. Then this is going to be executed again with a new random generation. I'm going to find S2. I'm going to find S3. I'm going to find S4. And you get it. You're going to get up to SB, S 100,000. Okay, and at the end, you get your nice sample of S. And that's it. Okay, that's it. Now, note here, well, I didn't do that in a function. I should have. I mean, it's not the end of the world, but maybe it would have been better to do this in a function. You will forgive me, I hope. Okay, so I just execute. Whoops. Where am I in my code? Okay, I just execute everything. And let's check. B is not found. Okay, I haven't declared this. Okay. It's taking a second. And then we should get, okay. Now, the theory tells us that the mean should be 400K. Okay, close enough. Standard deviation from the lecture slides, we had 315K. Okay, close enough. Let's have a look at the histogram. Okay, it looks like this. You see the shape is a bit strange. There's a mass at 0 that's quite important. So here, there's actually a non-trivial probability that there are 0 claims because, because out of 300 people, okay, this probability is quite small actually, but it's not 0, right? Out of 300 people, it's possible no one's going to claim because the probability of a claim is 1%. Okay, so I guess it is improbable that no one claims, but it's certainly not impossible. So there's this mass at 0, and for the rest, it seems to be relatively continuous. Now, what else? In the lecture, in the theory, what we've done is apply approximations here, apply the log normal approximation. But based on this shape, probably the log normal is not going to be very good. But let's check explicitly. Let's add to this histogram the curve of log normal. Now those parameters, they are exactly the values derived theoretically when we use the log normal approximation to this problem. So let's add this to our histogram. It's pretty bad. It's pretty bad. overall, it's pretty bad. Now on the tail here, for big values, maybe it's not so bad. So let's see. Let's find what we were here for. That was the big question we couldn't answer theoretically. We just could find an approximation. What's the probability that S exceeds 3 times its theoretical mean? Let's see. Well, how am I doing this in R? The syntax here is that this creates a vector of true, false, true, false, true, false. Okay, so every time, because remember S is a vector, every time S is bigger than this, there's going to be a true. And if you sum true and false, well, the trues have a value of 1 and the false have a value of 0. So this really gives you what you want. It gives you the number of time S exceeds the mean, and divide by B, it gives you the proportion. Okay, we get 0.02. Let me, in the slides, if you go to the slides, the normal approximation was 0.55%. And the log normal approximation was 2.688%. This is still an approximate number, but it's approximated from the real distribution of S. Okay. Now, I think let's increase this to 1 million. Okay, let's do this 1 million times. Now it's going to take a few seconds to compute, but I think we have the time. Okay, so here there's this icon that is telling me R is busy. Okay, because there's 1 million. We're simulating 1 million times, but then each simulations there's many simulations inside. So you can imagine it's taking a bit. That should be fine. In the meantime, you can take a sip of your favorite beverage. Okay, so now we have an answer. Let's check again. The mean should be even closer to the real value and the standard deviation as well. Oh, the histogram of 1 million observation. Okay, no, it's giving me. Very nice. And then lastly, okay, so I get a value here that was relatively similar to the one I had before. So the real value is something like 2%, 2.06%, maybe 2.1%. So you see, log normal approximation was better. Not amazing, but certainly better. And you see here on the tails, it's looking to do a decent job. Maybe would have been better for me to add a ECDF comparison, like the comparison of the CDF. Maybe you can do that yourself. Because I don't want this video to be too long. It's already pretty long. Let's do the last. Is it the last thing? Well, okay, 2 more things, but okay, 2 more things. Simulating. So we've simulated from the IRM, individual risk model. Let's simulate from the collective risk model. Okay, where now it's a bit different. The number of claims is itself random. Let's simulate. So this is again in the same spirit of what we've been doing. Let's simulate a situation that we're familiar with. The last example in the week 4 slides. Let's just review it quickly. Week 4, and again, we use some approximations. So this example, if the number of claims is Poisson, so it's random, it has a Poisson distribution, and the individual claims are exponential with those parameters. So here you have a compound Poisson. We use a normal approximation to estimate this specific probability. In fact, we did this with the normal approximation. We saw the normal approximation was terrible because, in fact, we were able here to derive the real probability. We used R to do this. That's a separate video. But we could find the exact number. But here again, for pedagogical value, let's simulate the situation and see if our simulation match what is the actual real number. Okay, so let's do that. Okay, it's quite easy. Again, let's do it in a function. I give it this name. Again, the arguments are the sample size and the parameters here. So let's not get confused. Lambda is the Poisson parameter and theta is the exponential parameter. First, I simulate my ends. But again, the point is that we're simulating a large sample of S. Okay, but S itself, every individual S is made of many X's. How many? Well, N. Okay, but I'm simulating a sample of N, which is the sample of the size of my simulations. N times I simulate a Poisson with parameter lambda. Now again, same strategy. I'm declaring an empty vector where I'm going to put all my S values, and inside the loop I can do that. So for every simulation, again, I represents each individual simulation. I have n of them. Now, maybe to be consistent in my notation, let's call this B. Okay, let's call this B. Because before I called B the number of simulations. So we want to be consistent, right? So I'm going to change. Now, of course, I'm going to forget somewhere to change it, but I think this should work. Okay. Okay. So what's the syntax here? Now, again, we deal with the case n equals 0 separately. And here, just to show you, you can use this function if else. So before you had this separate statement if else, but there's actually a function that allows you to do this. So if this is true, then return 0. Well, yes, if the number of claims is 0, the sum of all claim amounts should be 0. There hasn't been any claims. Otherwise, okay, so if this is false, it means there's at least one claim. Then the result for S should be the sum of n exponentials. And I, well, yes, because I'm doing this in a for loop, because I want to do this b times. Okay, so you're summing ni exponential, where each of them has the theta parameter. Okay, so hopefully that works. And by the way, just a comment that if else doesn't like this argument to be a vector. Okay, so I've encountered problems before where I tried to use this where this argument would be a vector, so it doesn't work. So just careful with that. Here we're fine because n, although don't be confused with what I just said, even though if it was not so clear. N is a vector, but of course ni, it's a specific value, so we're fine. Okay, but you could have not done this one shot with if else by feeding it a vector here. Maybe there's a way work around this, but I don't know it. Anyway, hopefully that works. At the end, of course, we return our sample. Then let's check. I'm going to create a sample of this compound Poisson. Okay, sample of size again 1 million, so it's taking a second. Can take another sip in my Mr. Happy cup. And then let's find, so this is exactly the probability we wanted. Again, you're summing how many times is S exceeding the threshold, and then you divide by the sample size. Okay, so I get the probability here. So it's an approximate probability because it's based on simulation, a million simulation, but the simulation is of the exact situation we have. So we get a probability of 1.07%. 1.07%. The real number was pretty much that. Well, it was to a four significant digit was 1.068. Okay, well here we have 1.070. Okay, but it is pretty close. Okay, which is obviously expected. I think that's all I want to say about this example. There's nothing, no additional complexity, but let's do one more example as a bonus, just that has one additional layer of complexity, nothing crazy. It's again simulating from the CRM, but now where the distribution for the severity is something discrete that we haven't, we don't have a function for this implemented in R. Okay, so how could you, at least in a simple case for a discrete random variable, how could you implement the random simulation of a discrete X? Let's do that. So this is a tutorial exercise called this. You know, the tutorial exercise, they have names, unique names. So let me just find it. Okay, in the tutorial, this would be in week 4. Yeah, so it's this one. It's this one called CP discrete severity. So basically, I want to simulate a S that has this distribution. Again, the frequency is Poisson, but here you see the severity is something like arbitrary. You know, probability to be 1 is 10%, probability to be 2 is 20%, probability to be 3 is 30%, probability to be 4 is 40%. How can I simulate that in R? It's not so hard. Let's do it. So again, let's do that in a function. Here you see my severity is given. There's no parameter to the severity distribution. So the only parameters are the sample size. And again, maybe are we trying to be coherent and changing this to B? I suppose. Yeah, let's do it. Okay, let's change B, then we change this to B everywhere. Okay. So what are we doing? First step is exactly the same. The simple, the number of claims is Poisson. But now I need to be able to simulate this X, which is discrete. Now, I don't have a simulator for X, but I'm going to create one. Again, I'm creating a function inside the function. I could have created this simulator elsewhere, but because it's very, the use of this for me is really narrow, I'm just declaring it inside the function. What I mean is I don't expect I'm going to be using this Rx elsewhere, so I might as well declare it inside the function. And here I hear thunder. I don't know if you hear it, but at least for me it was pretty loud. Anyway, what's happening here? Okay, I just want to be, that is a simple task. I just want to be able to simulate this random variable that takes 1 with probability 10%, 2 with probability 20%, blah, blah, blah. Okay, I'm doing this in a function. I'm going to use I suppose this is analogous to what we did in the Pareto case. So I'm not going to find explicitly the inverse CDF, but I suppose it's kind of the same strategy. Okay, I'm declaring this empty vector, which is going to host those values for X. Now, what's going to happen? I'm doing this. So I'm doing this m times. Yeah. Okay. This is m is just the number of times I'm doing it. Okay. It's not. It doesn't matter here. Okay. It doesn't matter what this is called. Maybe you could have called this n or whatever. But let's keep m. So the gist of it is here. If a uniform, so here I've declared a sample of size m of uniforms. What I want this function to return at the end is a sample of size m of x. But you see, if a uniform is smaller than 10%, sorry, yeah, it's smaller than 0.1, then I'm going to create x to be 1. Well, yes, because there's exactly 10% chance that a uniform is smaller than 0.1. If there's exactly 10% chance the uniform is smaller than 0.1, this is going to create an x that has exactly 10% chance of being 1. And so on. Else if the uniform is smaller than 0.3, but careful, if we have reached this step, it means that the uniform is bigger than 0.1. So if the uniform is bigger than 0.1, but smaller than 0.3, then give to my x the value of 2. Now you see, this means that x will have exactly a probability of 20% to be 2. Well, yes, because there's exactly a probability of 20% that we get here in the code, that u is bigger than 0.1, but smaller than 0.3, and so on. Else if u is bigger than 0.3, but smaller than 0.6, and this happens with probability 30%, then I'm going to let x be 3. This is going to yield that x will have a probability 30% to be 3. And lastly, the last case, so I just write else. I just write else because any other case, just get me x to be 4. And again, it works in the sense that if u is not bigger than 0.6, what did I say? If u is not smaller than 0.6, it means it's bigger than 0.6, but being bigger than 0.6 for a uniform has probability exactly 40%. So then this is going to create an x that has 40% probability to be 4. Okay, hopefully that was relatively clear. So here, I close the for loop. This function, again, I'm still inside the function Rx. Okay, so Rx for the random generation of X. Here I'm closing the function Rx. So this function now is usable inside my main function, which is this one. So then I can generate what I want, meaning I generate, again, an empty sample for S. I'm going to do B times what? Well, if Ni is 0, then again, my compound sum will be 0. There's nothing to sum because there's 0 claims. Otherwise, exactly like before, I'm going to sum Rx, which of course I can use because it's declared here. Rx is generating. So here, let's make sure we have the right parentheses. Rx n1 is generating n1, or I say n1, but ni is generating ni of those x's. Okay, so you see, let's do the example for, n1. Let's say that n1 is 2. Okay, let's say that n1 is 2. Then here, the first time, si will go here. Well, n1 is 2, so it's going to go here. It's going to sum what? Well, it's going to sum 2 randomly generated x. That's what S1 will be. And then et cetera, et cetera, et cetera, et cetera. At the end, you return S. Okay. And then I'm going to declare this function and see if it worked. I mean, by the way, here you could have checked first. Let's declare X first. Rx first. So I declare Rx. So I declare it outside of the function. So now I can use it. Rx exists. Now Rx, again, remember it's generating. Let's say I generate 10 times. It's generating observations that are randomly generated from 1 to 4, but of course without equal probability. If you want to make sure it worked, you could have a histogram of Rx. Let's say I do this 10,000 times. Seems to have worked because I have, I have 1,000 that are equal to 1, 2,000 that are equal to 2, and etc. Okay, so it seems to be working. Rx is working, and now I'm going to see that if the whole thing is working by generating my sample of the compound Poisson with this strange X. Okay, I've just generated it here. I can plot the histogram. Okay, that doesn't tell me much, but what I can check is, because we've in the tutorial, what have we found in the tutorial? Let's just check. In the tutorial, all that work we did was to find the probability S is smaller or equal to 4. And we have found that this was approximately, well, this is exactly the approximate, just mean that there's rounding, but besides rounding, this is an exact value. 44.78 or 44.79%. So let's check in our R, which is now R is an approximation because it's based on simulations. But let's see. Again, I'm summing how many times was S smaller or equal to 4. Can you see? Pretty close. Okay, 44.77%. Okay, let's here. Oh, I already had a sample of size. Oh no. Let's try 1 million. Might take a second. Might take 2 seconds. Asking a lot of R. Okay, and then well, it's actually not. Well, it's not even really better because it's similarly close. Okay, the real value again being 0.44788. Okay. I hope this was a bit instructive. Maybe you learned a few things you didn't know before. If not, maybe you saw again things you already knew. I'll stop this video here. It's already long enough, and I'll see you in the next one. So as usual, thanks for watching, and see you soon.